Okay, picture this. You're about to drop an ice cube into your drink, right? You watch it bob there on the surface. Seems simple.
Very simple, everyday physics.
Exactly. But what if I told you that simple act, ice floating on water, actually hints at this huge cosmic secret? Something that could help us understand the universe, maybe even life itself.
Because the ice out there, far beyond Earth, is, well, it's a completely different beast. Alien, almost. And incredibly important.
So today we're doing a deep dive into space ice, specifically something called low-density amorphous ice, LDA ice.
That's right, LDA. And it's dramatically different from the ice we all know. Understanding it is honestly becoming absolutely critical for figuring out some major cosmic puzzles.
Right, so our mission today, for you listening, is to pull out the really key bits of knowledge from the research. We want to explore how this space ice forms, what role it plays out there, and maybe even some surprising uses back here or, for future space missions.
Consider it your shortcut to getting up to speed on something pretty fascinating, but maybe a bit obscure.
Okay, let's start with that contrast then. Earth ice versus this space ice.
Okay, so Earth ice. Its defining thing is that hexagonal crystal lattice. Think snowflakes, glaciers, your ice cubes.
That regular ordered structure.
Exactly, structured orderly. And that specific hexagonal pattern is why solid ice is less dense than liquid water. It's why it floats.
A property that, it literally shapes our whole planet's climate, doesn't it?
Fundamentally, ecosystems, climate, yeah. But then you look out into space.
And it gets weird.
Yeah, it gets weird. Space ice, especially this LDA type, is totally different. Forget neat ordered crystals. Think glassy, disordered, a jumble of water molecules.
Glassy, like window glass.
Sort of, in the sense that it lacks that long-range crystal order. That's the LDA ice we find in really extreme places, like dense molecular clouds.
Stellar nurseries, basically, where stars and planets get started.
Precisely. So the big question is, how does it end up so different? And, why does that difference matter on a cosmic scale?
How do we even figure that out? We can't exactly scoop up ice from a nebula.
Not easily. So researchers, like a team at University College London, UCL, they use really sophisticated computer simulations.
Ah, okay. Virtual ice.
Kind of. They create these virtual boxes filled with water molecules. Then they cool them way down to minus 120 Celsius, like deep space. But crucially, they vary how fast they cool it.
Does the cooling speed matter that much?
Apparently, yes. It lets them mimic different conditions in space and see how the ice structure forms or doesn't form in response.
Okay, so what did these virtual ice experiments actually show them? Anything jump out?
Yeah, actually something quite surprising did. The simulation suggested that about 25% of this LDA ice isn't purely amorphous. It actually has tiny crystals embedded within it.
Wait, so it's not completely disordered. It's got little bits of crystal structure hidden inside.
Exactly. It's mixed phase. And while it's indirect evidence from simulations, it strongly suggests that the space ice, it kind of holds a memory of how it first formed.
A memory? That sounds
right.
Amazing. What does that mean, a memory in ice? Like it remembers the temperature or pressure?
Pretty much, yeah. The conditions present when it originally solidified the specific temperature, the pressure environment seemed to be sort of imprinted in that mix of amorphous and crystalline structure.
Wow.
And if you connect that to the big picture, this subtle internal structure, this memory, is incredibly important. Michael Davies, who led that UCL research, put it really well. He said, ice influences how planets form, how galaxies evolve, and how interstellar matter migrates.
So it's not just passive stuff floating around, it's actively shaping things. A cosmic architect, you called it.
That's a good way to think about it. It's an active participant.
Okay, so if the ice-forming planets, those initial building blocks, is partly crystalline, that changes how we think about early solar systems forming, right? The structure, the composition of new planets.
Absolutely. It affects how materials stick together, how dense they are, maybe even what chemicals get trapped. But think smaller scale, too. What about the ingredients for life?
Ah, okay. You're heading towards the panspermia idea.
Exactly. The theory that life's building blocks, amino acids, organics, might have hitched a ride to Earth on icy comets or asteroids.
So how does this mixed phase ice affect that delivery service if it's got crystals in it?
Well, Davies argues it might mean fewer cozy pockets for trapping those delicate organic molecules. The crystals take up space, maybe making it slightly less efficient as a carrier.
Less efficient. So bad news for panspermia.
Not necessarily a dead end, it's more nuanced. The research is clear that the amorphous parts of the LDA ice still provide crucial hiding spots, little niches where these molecules could be shielded from radiation and harsh conditions.
Okay, so it's complicated. Fewer pockets overall, maybe, but still places for life's precursors to hang out.
Precisely. It's not a simple yes or no answer, and that kind of nuance, that complexity in disordered materials, it actually pops up elsewhere too.
Where else?
In materials science, surprisingly, there's a whole class of materials called ultra-stable glasses.
Ultra-stable glasses.
Yeah.
Are these related to everyday glass?
In principle, yes. They're amorphous, lacking that crystal structure, but engineered for specific properties. Think the glass fibers in fiber optic cables. Super important.
Right, for the internet, communications. And OLED screens, too, you mentioned.
Yes, the screens in modern TVs, phones, they rely on these very precisely made, disordered structures to work efficiently.
Huh. I never thought about my phone screen having anything in common with space ice.
Well, Professor Christoph Salzman at UCL Chemistry raises this really interesting question linking them. He asks, basically, if tiny unwanted crystals affect space ice properties, could carefully removing tiny crystals from our engineered amorphous materials, like those in fiber optics or OLEDs, actually boost their performance?
So understanding the flaws, the tiny crystals in space ice, could actually help us improve technology here on Earth.
That's the provocative idea, yeah. The fundamental physics of how these disordered structures behave, whether in a nebula or a network cable, seems surprisingly connected. It just shows how much we can learn from studying these extreme environments.
It really makes you rethink things.
Yeah.
Okay, so we've talked about the past, how ice forms, how it affects planets, maybe life. What about the future? Is space ice just there, or could we actually use it?
That's the next frontier, really. Thinking of ice not just as a scientific curiosity, but as a resource for future space exploration.
A resource, like water is a resource, obviously, but more than that.
Potentially, yes. Think of it as a high-performance resource. The research highlights its ability to hold hydrogen and oxygen.
Rocket fuel components.
Exactly. If you can extract them, you potentially have propellant depots out in space. And beyond fuel, think about radiation shielding.
Yeah, radiation is a huge problem for long missions.
A huge problem. Thick layers of ice could act as a natural, effective shield for habitats or spacecraft. Imagine engineering structures using specific forms of ice found out there.
That really sparks the imagination. What breakthroughs could come from learning to harness ice beyond Earth? It's not just frozen water anymore.
It really isn't. So just to recap the main points for everyone listening.
Good idea. Let's nail down the key takeaways.
Okay, first, the big difference. Earth ice has that neat hexagonal crystal structure, makes it float. Space ice, particularly LDA, is mostly glassy, disordered.
Right. Amorphous. Second takeaway.
That new research showing LDA isn't purely amorphous, it's often mixed phase with embedded crystals. And this suggests it holds a kind of memory of its formation.
Okay, memory stored in the ice structure. Third point.
The impact on panspermia. That mixed phase structure might mean fewer spots for organic molecules overall, but the amorphous regions do still provide essential niches. So it's nuanced.
Nuanced, right. Not simple. And finally.
That surprising link to materials science. Understanding space ice might, unexpectedly, help us improve things like fiber optics and display screens through the parallel with ultra-stable glasses.
From an ice cube in your drink.
All the way to the frozen clouds where stars are born, and maybe back to the phone in your pocket. The structure of ice, even its imperfections, turns out to be incredibly profound.
It really does. It shows how something we think is so simple is actually this complex cosmic architect, as you said.
Yeah.
So this deep dive really hammers home how these tiny details, these little crystals hidden in space ice, could unlock huge things. It makes you wonder, doesn't it? What could this mean for actually designing future missions? If we could engineer materials based on this, or know exactly what kind of ice to look for as a resource, could that totally change how we build spacecraft, or even where and how we search for signs of life? Knowing these details makes the universe feel, well, even bigger with possibilities.
Absolutely. Keep asking those questions. Keep looking at the details. There's always more to discover, more connections waiting to be found. That's the fun of it, isn't it? Another deep dive waiting to happen.